Hello, I'm John Doherty. This video discusses the solution of a well-posed inverse problem. Calibration of a groundwater model is inherently an ill-posed inverse problem. Normally, when using PEST, we allow this problem to be ill-posed. However, there is some value in understanding the mathematics behind the older way of doing things, whereby regularization is entirely manual. Now, for some of this video, I'm going to be writing equations on a tablet rather than presenting them on a slideshow. Personally, I find it easier to understand mathematics when equations evolve as they are described. I hope that this works for you. Calibration of a groundwater model is an inherently ill-posed problem. The medium through which groundwater flows is heterogeneous. The conditions, the stresses which drive its flow, the boundary conditions that border its flow are all heterogeneous. There are far more hydraulic properties that govern the movement of groundwater models, the groundwater, that can never be estimated uniquely. Yet, when we calibrate a groundwater model, we seek a unique solution to this inherently very ill-posed inverse problem. The reasons for doing this have been discussed in another video. To achieve a unique solution to a fundamentally ill-posed inverse problem, we have to adopt a strategy that is referred to as regularization. Regularization, then, is the term that mathematicians give to whatever it takes to achieve uniqueness of solution of an inverse problem which is fundamentally ill-posed. Regularization strategies fall into three broad categories, all of which are supported by PEST. One of these is Tikhonov regularization. Another is subspace methods, of which singular value decomposition is the flagship. And then there is manual regularization, which is actually the subject of this video. So, to achieve uniqueness using manual methods, there are many strategies that we can use. For example, we may have hundreds of parameters that we would like to estimate, hundreds of parameters that are unknown. We may decide to fix most of those at a certain value and just estimate a few, based on the assumption that if we estimate more than a few, the inverse problem will not be unique. Alternatively, or as well, we may divide our model domain into large zones of assumed piecewise constancy with sharp boundaries between those zones, on the basis that the fewer the zones into which we subdivide the model domain, the fewer parameters we'll have to estimate, and the more likely it is that the inverse problem which we thereby design will be well posed. We could fix ratios between parameters. We could estimate some and let other parameters ride on the backs of those we estimate by maintaining fixed ratios to those we estimate. And of course, there are many other parameterization simplification strategies as well. Whatever we do, though, there's going to be problems. As we'll talk about in other videos, one of the benefits of numerical and mathematical regularization is that not only does it lower the number of subjective decisions we have to make, but it does provide, if we do it properly, some guarantee that when we solve the inverse problem, we achieve a minimum error variance solution to that inverse problem. It's very difficult to provide that assurance if we are undertaking regularization through manual means. We have many decisions to make and we can't be sure that we're making those decisions the best way. For example, am I estimating too few parameters or too many parameters? Am I underfitting or overfitting. I mightn't find out until I actually try to solve the inverse problem, discover that I'm not getting a good enough fit with the data, or that I'm getting silly parameter values through overfitting, and then I've got to go back and start again. And then what about the values that I assign to fixed parameters? If I estimate some parameters while holding other parameters fixed, what if I assign incorrect values to the fixed parameters? Do the values that that the inversion process then bestows on adjustable parameters, are they wrong in compensation for the wrong values that I attribute to fixed parameters? All of these problems beset us when we do manual regularization. And then there's the problem of post-calibration uncertainty analysis. As we discuss elsewhere, most predictions made by a groundwater model are going to be quite uncertain, some more uncertain than others. And if a prediction of management interest is sensitive to parameters that I've had to eradicate from the inverse problem on the basis that the inverse problem wouldn't be unique if they were included in that problem, how can I be sure that the uncertainty analysis has integrity? In fact, if a prediction is sensitive to a parameter that can't be estimated, that will add to the uncertainty of that prediction. Yet, when undertaking manual regularization, the parameters that can't be estimated need to be removed from the inverse problem. So presumably they have to be added back into the problem when I'm doing post-calibration uncertainty analysis. But am I adding in enough parameters to that post-calibration uncertainty analysis process? We can never be sure. In what follows then, we're going to base our analysis on this equation. I'm going to assume that the model is linear. That is, that the relationship between model outputs and parameters can be described by the operation of a matrix on a vector. The vector P will hold the parameters that I'm estimating. The vector H will hold the calibration data set, the measurements of head in wells or fluxes, which I'm using as a basis for estimating the parameters in the vector P. The vector epsilon will contain noise associated with my field measurements. The vector X, which is very much like a sensitivity matrix, is the matrix which will describe the operation of the model on my parameters to produce outputs that correspond to measurements which comprise a calibration data set. So what this simple linear equation says is the action of the model on my parameters plus measurement noise is what I observe. And even though this equation is simple and it's linear and the world is nonlinear, equations similar to this are at the heart of PEST actually, and in ways which we'll find out in other videos, we'll discover how PEST can adjust its behaviour to accommodate the fact that a model is in fact nonlinear. This picture here summarises our situation. Here's our matrix X, and notice that this matrix is long in the vertical direction. That is, we are assuming that we have less parameters than we do field measurements. The length of the vector epsilon is of course the same as the length of the vector H, because this is the noise associated with the observations. But to have a well-posed inverse problem, we must be estimating fewer parameters than observations which comprise the calibration data set. We cannot estimate more parameters than we have data. Just because we're trying to estimate less parameters than we have data, it is not a foregone conclusion that those parameters are uniquely estimable, but it is a necessary condition for an inverse problem to be well posed that we estimate less parameters than data. So let's start with our fundamental equation. H equals xp plus epsilon. Our task is to estimate P from H. Let's make life easier for ourselves to start with by assuming that there's no noise in the calibration data set. I still can't calculate P from H using that equation because the X matrix is long in the vertical direction. And there is no inverse of a matrix that is long in the vertical direction. Only a square matrix has an inverse. So the first thing I have to do is create a square matrix. Let me do that by multiplying both sides of this equation by xt. Xt is the transpose of x. And when I do that, I end up with a square matrix that has the same number of rows and columns as does the vector p. So let me multiply both sides of the above equation by xt. xth equals xt x p. Now, if xtx has an inverse, I can multiply both sides of that equation by the inverse of xtx. Let's assume that it does have an inverse. In fact, the whole purpose of manual regularization is to assume that xtx is to create the circumstances whereby xtx has an inverse. If xtx doesn't have an inverse, then I have not done my regularization properly. So, xtx inverse -1 xth equals xtx inverse xtx p. Now, because we have an inverse multiplied by the matrix, I can cross these two out. Let me bring P over to the left-hand side. Let me put a little hat over it to signify that it's just been estimated. P equals xtx -1 xth. And I've now solved the inverse problem. I have now estimated P from H. So let's go back up to the top here and write down our original equation, the equation which describes the situation that we're in when we're trying to calibrate a model. H equals xp plus epsilon. Now I'm not ignoring the fact that there's noise associated with the calibration data set. Let me substitute that into here and write some more equations. So making that substitution, I have P equals xtx -1 xt xp plus xtx -1 xt epsilon. Now in this equation, this P here is my estimated P, my estimated parameters. This P here is the real parameters the parameters that I will never know, but whose job it is for me to estimate. Once again, we have an inverse next to the matrix of which it's the inverse, so that I can write p hat equals p plus xtx negative 1 xt epsilon, or to put it another way, p hat minus p, that is, the error in my parameters that I've incurred through solving that inverse problem, equals xtx negative 1 xt epsilon. So, not only have we solved the inverse problem, there's the equation that we use to obtain our estimated set of parameters, but I also have an equation for the error in those parameters. The problem is that the error in those parameters depends on the noise in the data, and I do not know the noise in the data. This is a random number of which I have no knowledge. So it's satisfying to have derived an equation for parameter error, but we can't calculate the error in the parameters. If we could, we'd simply correct the parameters we've estimated for the error. And this is something that I can't do because I do not know epsilon. Let's pause for a moment here and think about what we've done, however. We've said that when we've calibrated a model, all the error in our parameters is a function of measurement noise. Now actually, a moment's reflection says that can't be the case. If we've had to create a simplified parameter set in order to create a situation where this inverse here exists, there has to be more error in the parameters than that arising solely from noise in the calibration data set. What about the error incurred through having to simplify the parameter set? Unfortunately, one of the problems associated with doing manual regularization is that that error cannot appear in any equation because the simplification is done by us and is not done mathematically, and therein lies a problem. So let's continue with this process. We have an equation for our parameter error, but we can't actually use that equation because we don't know epsilon. However, ideally, and I'll draw a line down here, ideally we do know, if not epsilon, we do know C epsilon. This is the covariance matrix of measurement noise. Ideally, we know something about the statistics of measurement noise. This will then allow us not to calculate the error in our parameters, but will allow us to calculate the statistics of the error in our parameters. That is, the propensity for the parameters to be in error. Now, in another video we showed a very important equation. We said that if we have a random vector x and we calculate another vector y from x, then y is random and the covariance matrix of y can be calculated from the covariance matrix of x using this equation. Let's apply that. So let's take this equation here as our starting point, and let's calculate the propensity for error in our parameters, that is the covariance matrix of parameter error. So covariance matrix of parameter error, C p hat minus p equals xtx -1 xt c epsilon x xtx -1. Now let me make an assumption to make the next equation easy. Let me assume that C epsilon equals sigma r squared I. That is, I'm assuming that the noise associated with each measurement is independent of the noise associated with every other measurement, and I'm assuming that the noise associated with all measurements is the same and has a standard deviation of sigma r. Now let me substitute that into this equation so that I have C p minus p equals sigma r squared xtx -1 xtx xtx inverse. That crosses out with that, and I have my equation for the covariance matrix of parameter error Here it is. So not only now have I estimated my parameters over here, I have now come up with an equation that will give me the uncertainty of those parameters, which I'm equating to the propensity for error in those parameters. Once again, it all depends on the noise in the data. That sort of defies logic, but that's what we're left with when we're doing calibration, where the instrument for our regularization is manual simplification of the parameter set. Let's take this one step further now. Suppose I have to make a prediction with my model. Let's call that prediction S. It's a scalar, it's just a number. And let's say that the sensitivity of that prediction to the parameters is in this vector here, y. So that vector y contains the sensitivity of this vector y here, contains the sensitivity of S to every one of my parameters. When I make a prediction with my calibrated model, however, I don't get to use the true parameters. I have to use estimated parameters. So there's error in my prediction. Putting those two equations together, subtracting one from the other, S minus S equals YT P minus P. So that this equation here expresses the error in my prediction. But I don't know the error in my prediction because I don't know the error in my parameters. But I can say something about my propensity for predictive error. So let's now substitute this equation into here. But first, what I have to do is I have to use this equation again to derive the covariance matrix for parameter error. Now, because S is a scalar, this is just the variance of predictive error. I should have said predictive rather than parameter before. So the variance of predictive error equals sigma x squared, because a matrix that has only one element is a scalar, and a covariance matrix that has only one element is the variance of the quantity whose uncertainty is being described, and that equals yt cp minus p y, just using this equation. Now I substitute that into there to say that my predictive error variance, which we can loosely equate to the uncertainty of any prediction, of a prediction I make with this calibrated model, equals sigma squared r yt, just rub that out, xtx negative 1 yt y. So now what have I done? I've calibrated my model. Put that back in. I've calibrated my model and I've estimated a set of parameters for it. I've quantified the uncertainty associated with the parameters that I've just estimated, and when I make a prediction with this model, I have quantified the uncertainty associated with that prediction. But, as stated before, all uncertainty in the parameters, all uncertainty in the prediction ultimately is calculable from noise in the data. We have ignored in this formulation any errors in the parameters that arise through the simplification that is necessary to guarantee that that negative 1 exists. And that is a big problem with manual regularization. So let's write out the equations that we've been dealing with up to now at the top of the page. Here is the fundamental equation that defines our problem. And we've established that our estimated parameter set can be obtained through this equation. And that the covariance matrix of our parameters, covariance matrix of parameter error, can be obtained through this equation. However, in deriving this equation here, we assumed that measurement noise was 0. Now let's be a little bit more realistic. So, let's say that this is a certain model output, say the head calculated in a well as it varies with time. Let's say that these are corresponding head measurements in that well. Let's assume that this last measurement is HI. This is the ith measurement. I'll just make that a little bit clearer. This is the ith measurement. We define the difference, this distance here, the difference between a field measurement and a corresponding model output. We are going to say this is the ith residual, which I'm specifying as R. So Ri equals H minus XP I. The difference between the measurement and the corresponding model output. Recognizing that noise that's associated with the calibration data set, I'm now going to reformulate the inverse problem as one of getting the best fit with the data, minimizing misfit, minimizing residuals. To do that, I'm going to define an objective function, phi equals the sum of squared residuals, or to put it another way, equals H minus XP transpose H minus XP. And I'm going to say that I have solved the inverse problem. I've estimated the set of parameters which I deem to calibrate that model when I minimize this objective function. With a little bit of matrix algebra, it can be shown that minimization of the objective function leads me to a set of parameter values p hat which are provided by exactly the same equation as I had before. Again, everything relies on the existence of this inverse, which has to be manufactured as an outcome of the manual regularization process which precedes, which gives us this equation. Now let's get a little bit more complicated. Let's say that the noise associated with my calibration data set is not the same for every measurement. Let's say, for example, that there's more noise associated with this measurement than with this measurement. Let's say, therefore, that if I can't fit both, I'd rather fit this one here than this one here, on account of the fact that this measurement here is more credible. In that case, I can reformulate the inverse problem in a way that tries to tell the inverse problem, fit this one in preference to this one if you can't fit them both. And the way we do that is to use measurement weights. So I'm now going to redefine my objective function to reflect the fact that I am trying to discriminate between measurements that I do trust and measurements that I don't. So I'm going to say my objective function is now the sum of weighted residuals, sum of Wi Ri squared. Therefore, if there's a compromise, the residuals with the highest weights associated with them will be better fit. It can be shown fairly easily that the solution to the inverse problem now becomes p hat equals xt qx negative 1 xt qh, where q is a matrix, a diagonal matrix, where the weights are featured on the diagonal of that matrix, and everything here is 0. In that case, it's also easily shown that my covariance matrix for parameter error, Cp hat minus P, is slightly different. It is now sigma r squared xt qx -1. And it can also be shown with a little more difficulty that my solution to the inverse problem achieved through this equation is the solution of minimum error variance if, and only if, Q is chosen to be proportional to the inverse of the covariance matrix of measurement noise. In practice, what this means is that I use higher weights when the noise is less, lower weights when the noise is higher. Ideally, the weight associated with each observation should be the inverse of the standard deviation of measurement noise associated with that observation. That is, Wi, the weight associated with the ith observation, is proportional to the standard deviation of measurement noise associated with that observation raised to the -1. So let's write our equations once again. This is the fundamental equation that we're using to define our inverse problem. The outcome of manual regularization that makes that inverse problem well posed. We say that we estimate our parameters using this equation, where our Q matrix is our weight matrix, and then we can derive our covariance matrix of parameter error using this equation here. We also said that by making a choice that Q, we choose our weight matrix, is proportional to the inverse covariance matrix of measurement noise, we obtain a solution of minimum error variance for the parameters. We've minimized our potential for parameter error. So that is, we choose Q equals sigma r squared c -1 epsilon. Now, normally we assume that measurement noise can be characterized by a diagonal covariance matrix, and hence that means that if this is diagonal, Q will be diagonal. And by assuming that measurement noise is characterized by a diagonal covariance matrix, we are assuming that the noise associated with any one measurement is statistically independent of the noise associated with any other measurement. Now, that's normally a bit of a problem that will be addressed in other videos. Most of our model to measurement misfit when we calibrate a model isn't due to measurement noise, it's due to structural defects of the model that we're calibrating, and often these defects have been compounded by the necessity to establish a simplified parameterization scheme in order that this equation applies, and in order that this inverse exists. Hence, C epsilon, if we're going to say that epsilon characterizes all misfit, will not be a diagonal matrix. And hence Q should not be diagonal if we're going to establish a minimum error variance solution to the inverse problem. This is normally ignored. So we solve our inverse problem by minimizing an objective function phi, which, taking weights into account, equals the sum of wi squared, and the use of weights like this assumes a diagonal Q matrix that equals the RTQR equals H minus XP TQ H minus XP. Now, normally we do not know ahead of time what our fit will be. We don't know when we minimize the objective function what that final objective function will be. So we may have assumed that Q is proportional to the inverse of C epsilon. In practice, we don't know what this proportionality constant is. Fortunately, we can find out what that proportionality constant is after we've minimized the objective function. So, once we've minimized the objective function, we can then divide that by n minus m, where n is the number of observations and m is the number of parameters that we're estimating, and that gives us an estimate of sigma squared r. So our job then is to choose a Q matrix, that is, choose weights on the assumption that Q is diagonal, that we use in this equation. We then minimize the objective function. We minimize the objective function. From the minimized objective function, we calculate sigma r squared, sometimes called our reference variance. Then we substitute it into this equation to obtain our covariance matrix of parameter error. And then we have solved the inverse problem of model calibration under conditions in which we've undertaken manual regularization. So here is our workflow. Here's the equation which characterizes the system, which defines the inverse problem that we have to solve. We select a weighting strategy embodied in this matrix Q. And we choose that, taking notice of what we think is the uncertainties, the errors in the measurements that accompany the calibration dataset. Once we've chosen our weights, we then have an objective function which we can minimize. On minimizing that objective function, we obtain a set of estimated parameters. On the basis of the minimized objective function, I can calculate the reference variance, the proportionality constant between my weight matrix and what I presume to be the covariance matrix of measurement noise. And once I've calculated that, I can calculate the covariance matrix of parameter error, that is, the uncertainties in the parameters that I have just estimated. All of this, the maths that we saw previously and the issues we're going to talk about now, are explained in the PEST book, which is downloadable from www.pesthomepage.org. So far, we've been talking about linear models. Models in which the relationship between parameters and outputs, which correspond to the calibration data set, can be described by the operation of a matrix. Of course, this does not apply to real-world environmental models. We still use the theory that we have been talking about, but it has to be modified to accommodate the nonlinear situations in which we work. If my model is linear, then the contours of the objective function are hyperellipsoids. If I've only got two parameters, if I'm working in a two-parameter space, I can draw these as ellipses. My task then, in trying to solve the inverse problem, my task in estimating the two parameters that characterize a two-parameter inverse problem is to find this point here, the minimum of the objective function, the lowest point in this objective function surface, the contours of which are elliptical. If I'm working with a nonlinear model, the principle is the same, but the shapes of those contours are very different. They are no longer elliptical. They can have any shape. But at this stage, I'm assuming that we are still working with a well-posed inverse problem. Implied in that is that these contours have a minimum. There is a minimum at the center of these contours, and that these contours close, so that we can find an optimal set of parameters, a minimum error variant set of parameters, P1 and P2, through finding the lowest point in the objective function surface. This is the equation we've been using up until now, where we've had a matrix operation on our parameters to characterize the relationship between parameters and model outputs which correspond to the calibration data set, whose members are encapsulated in this H vector. Now I will use a slightly different equation where I've written x as an operator. So it's saying a very similar thing. What we observe in the field is the action of the model on the parameters plus measurement noise. But by writing it this way, I'm signifying that we are no longer looking at a matrix operation on the parameters. So let's look at the ways now in which we modify this theory so that PEST and PEST++ can undertake nonlinear parameter estimation. The first modification is that I no longer estimate my parameters in one step. I have to actually estimate changes in parameters in many steps. Let's see how this works. This is my new equation, but if I'm going to apply the theory that we've been talking about so far, I have to linearize this equation. That is, somehow or other, I have to replace this nonlinear operation with a linear operation, that is, a matrix operation. Firstly, I start off with an initial set of parameter values. I'm designating these as P with a subscript of 0, and the operation of the model gives me model outputs corresponding to members of the calibration data set. I am representing those model outputs as O with a subscript of 0. These are my initial set of parameters, and these are the set of outputs which correspond to those initial parameters. Then, using a theorem called Taylor's theorem, I can replace this operation with a matrix if I decide that I'm not actually calculating model outputs with a new set of parameters, but rather I am calculating changes to model outputs on the basis of changes of parameters, and the relationship between the changed outputs and the changed parameters, if I don't change those parameters by too much, the relationship can be described as a matrix operation, and this matrix is called the Jacobian matrix, or often the sensitivity matrix. So now I'm looking at changes to parameters and how changes to model outputs are calculated from those changes, and the relationship, if those changes aren't too great, is approximately linear. The Jacobian matrix, then, is a matrix of partial derivatives. The first column of the Jacobian matrix is the partial derivative of all model outputs with respect to the first parameter whose value I am estimating through solution of the inverse problem. The second column is the partial derivative of all model outputs with respect to the second parameter, and so on. Then, once I have linearized my model, I can apply the same equation that we have been using up until now to calculate an upgraded set of parameters. However, instead of having h here, I have the current set of residuals. So on the basis of the current model to measurement mismatch, I calculate a better set of parameters for which the mismatch will be less. So the next question is, how do I obtain that Jacobian matrix? If a model is sophisticated to calculate partial derivatives itself, it can provide that matrix. Most models that we deal with do not have this capability, so PEST has to calculate that matrix itself. It does so in an approximate manner. It varies each parameter in turn just by a little bit. So it varies the first parameter a little bit, runs the model, has a look at the changes to model outputs, divides changes to model outputs by the change in the parameter, and that then becomes an approximation to the partial derivative with respect to the first parameter. In other slideshows, we'll talk about how this can become a little bit more sophisticated. What this means, however, is that to fill a Jacobian matrix, we've incurred a numerical burden. We have to run the model at least once for every parameter that we are estimating through the inversion process. The second way that we have to accommodate model nonlinearity is to recognize that because we're dealing with upgrades to parameters and not estimating the optimal parameters directly, this whole procedure becomes iterative. That is, it has to be repeated many times. We start with our initial parameter estimates. Calculate a Jacobian matrix. Use that Jacobian matrix to calculate an upgrade vector. We obtain a new set of parameters. Calculate another Jacobian matrix. And so it goes until we eventually find the minimum of the objective function. This incurs an even greater numerical burden. For now, we have to calculate that Jacobian matrix not just once, but every time we need to do a parameter upgrade until we reach the minimum of the objective function. Thirdly, we have to modify the equation that we have been using just slightly. You see how I've added this term to this matrix before we do the inversion? This lambda value is called the Marquardt parameter, or the Marquardt-Liebenberg parameter. This lambda I is the identity matrix. The addition of lambda I means that I add lambda to the diagonal of this JTQJ matrix. It can be shown that if lambda is large enough, my parameter upgrade is straight downhill, straight down the gradient of the objective function. This is called the method of steepest descent. And indeed, if I'm far away from the minimum of the objective function, and I have a nonlinear model, and I want to wander down this objective function terrain till I reach the minimum, when I'm a long way from that minimum, going straight downhill is optimal. However, as I approach the minimum, I want to be more sophisticated and use the equations that we've been talking about up to now without the Marquardt lambda. Those equations are much better for finding the minimum of the objective function where objective function contours are elongate like this. So ideally, the Marquardt lambda should start off large, but it should decrease as we approach the objective function minimum. If it doesn't decrease, we have a bit of a problem. That problem is that the method of steepest descent is not very good at finding its way into these narrow valleys in parameter space. We have a phenomenon which mathematicians sometimes call hemstitching, where we just bounce across this valley. So it is important that as we approach the minimum of the objective function, particularly if there's a large degree of correlation between the parameters and these contours are somewhat elongate, it is good that the Marquardt lambda reduces so that we can find our way into this valley and therefore to the minimum of the objective function. Another step that we have to take when we're living in a nonlinear world is that we have to impose limits on how much parameters are allowed to change during any iteration of the inversion process. So here are our initial parameter values, and suppose that objective function gradients are not very steep out here in this nonlinear model terrain. We may then calculate that the parameters need to change a long way if we're going to change the objective function by much. We may do a calculation using our traditional equations, the ones that we've been talking about up to now, and we may overshoot the minimum by a long way because the gradients have all changed by the time we get down here, where we need to find our way into here, where the minimum of the objective function is. Perhaps the gradients of the objective function are low here again, and then, using the equations we've been dealing with up to now, we may overshoot again. This can be circumvented by limiting how much parameters are allowed to change during any iteration, and by imposing sensible limits on parameter changes, we can find our way to the minimum of the objective function. Finally, we have to recognize that when we calculate the covariance matrix of parameter error, we have to recognize that this is only approximately correct when we calculate it with a Jacobian matrix. The model is not linear. Normally, we calculate a Jacobian matrix once we've reached the minimum of the objective function using best parameter values and on the basis of that Jacobian matrix we can calculate our matrix, our covariance matrix of parameter error. But if our model is nonlinear, the definition of nonlinearity is that this Jacobian matrix is sensitive, is dependent on the actual values of the parameters. Therefore, the covariance matrix of parameter error, the uncertainties that we associate with the parameters, is only approximate. However, often they're not a bad approximation. I want to talk a little now about the parameter covariance matrix, or the covariance matrix of parameter error that we can calculate after we've solved the inverse problem. As we've already said, this is only an approximate characterization of the uncertainties of parameters that we've just estimated. However, it has uses other than just characterizing parameter uncertainty. It can tell us a lot about the quality of our manual regularization. When we undertake manual regularization, we have some problems. We have to decide how many parameters we're estimating. If we estimate too few, we don't get a good fit with the calibration data set. If we estimate too many, we may overfit. Now, overfitting is the subject of another video. If we estimate too many parameters, not only may we overfit, but we may be trying to solve an inverse problem which is non-unique. In that case, the matrix which PEST has to invert to calculate parameter upgrades, it may not be able to invert it at all. PEST may not be able to solve that problem. So here is the parameter error covariance matrix that I'm just writing down its individual elements here. Now we need to look at this matrix to find out whether we are estimating too many parameters. If we're estimating too few, it will be apparent through the fact that we haven't fit the data very well. Have we estimated too many? That's a question that has to be answered in slightly more subtle ways. One of the ways that we can gain insights into this problem is to calculate from this parameter error covariance matrix a parameter correlation coefficient matrix. This matrix can be calculated from this matrix very simply. I'm just illustrating here with a 2 by 2 matrix, but if we've got a 3 by 3 or an m by m parameter error covariance matrix, we will have a 3 by 3 or m by m correlation coefficient matrix. Elements of these two matrices are matched on a one-to-one basis. Each element of the correlation coefficient matrix is calculated from the corresponding element of the parameter covariance matrix using this formula. Basically, what it means is this. The diagonal elements of the correlation coefficient matrix will always be 1. The off-diagonal elements of the correlation coefficient matrix can range between 1 and -1. To the extent that any element, off-diagonal element, approaches 1 or -1, the corresponding parameters are becoming excessively correlated in a post-calibration sense. This is another way of saying that the information content of the calibration dataset cannot estimate those parameters individually. It can only estimate values for combinations of those parameters. It cannot separate them out individually. The correlation coefficient matrix can tell us which parameters are excessively correlated. We, armed with that information, then have to probably fix one of those parameters and let the inversion process estimate the other, because the correlation coefficient matrix has told us if one of these off-diagonal elements approaches 1 or -1, that the corresponding parameters cannot be separated on the basis of the information content of the calibration data set. Ideally, we'd like this situation. Here are our objective function contours again. No correlation here. But if we've got a situation like this, where the two parameters have a correlation coefficient that approaches 1, this tells us that we have long, narrow objective function contours. That any values for parameters in here give us an objective function that is still very small. The minimum may be here, but the objective function values are very small all through here. As long as P1 equals P2, we have almost minimized the objective function. Therefore, the information content of the calibration data set can tell us that P1 probably equals P2, but it cannot tell us what P1 and P2 are. We then have to assign a value to one of them and let the inversion process estimate the other, because the inversion process cannot estimate both together based on the current content of the calibration data set. A similar story here. The inversion process cannot separate parameter values that lie along this line. It tells us that parameter values have to sum to the sum value that it has identified, but it hasn't told us what the values of the individual parameters are. That is beyond the reach of the inversion process. Now, at best, we have just got high uncertainties associated with P1 and P2 because of this post-calibration correlation. At worst, these contours mightn't close, in which case we've got a non-unique inverse problem, and PEST may not work because the matrix that it has to invert can't be inverted, because if we have non-uniqueness, we have not regularized, and we do not have a well-posed inverse problem. And the methodologies which we are discussing in this video rely on being able to invert a matrix, as we have discussed, and that matrix cannot be inverted if the inverse problem is non-unique or approaching non-uniqueness. Perhaps the best way to gauge the health of an inverse problem as far as non-uniqueness is concerned is to look at the eigenvalues and the eigenvectors of this covariance matrix. Now, this is not the place to talk too much about eigenvectors and eigenvalues. All I'll say at the moment is that eigenvectors and eigenvalues are the solutions to this matrix equation. They crop up everywhere in matrix analysis. In our case, they have some very special characteristics. Firstly, we're dealing with a positive definite matrix when we're dealing with a parameter covariance matrix. An M by M positive definite matrix has M eigenvectors, which are orthogonal to each other, and corresponding to each eigenvector is an eigenvalue. Eigenvectors and eigenvalues occur in pairs. An eigenvector has a corresponding eigenvalue. A nice quality about the eigenvectors of a covariance matrix is that they point along the principal semi-axes of the ellipses that the objective function contours form if the model is linear. So if we've got a two-parameter problem, we've got two eigenvectors, one pointing in the long direction of this elongate ellipse defined by objective function contours, the other pointing in the opposite direction. And the square root of the eigenvalue is proportional to the length of the semi-axes of these ellipses. Now there's some important qualities emerge from this. If the ratio of lowest to highest eigenvalue is very large, that means that we've got a long and narrow ellipse. That means we've got incipient non-uniqueness. That means we've got parameters which are highly correlated, which cannot be separated through the inversion process because the calibration data set doesn't have the information to do so. Knowing the fact that the ratio of our lowest to highest eigenvalue is very small tells us that perhaps we are estimating too many parameters through what we thought was a well-posed inverse problem. When PEST solves the inverse problem, as we have just said, it supplements this matrix by adding terms to the diagonal before it does an inversion. So even if an inverse problem is non-unique, PEST can often still obtain parameter values corresponding to a minimum of the objective function. It can still invert a matrix which really shouldn't be invertible if we didn't add diagonal terms, didn't add terms to the diagonal of that matrix. However, under those circumstances, the values that it estimates for the parameters will probably not be of minimum error variance. Therefore, if PEST is still able to solve an inverse problem which is non-unique or nearly non-unique, and if it is still able to calculate this covariance matrix of parameter error, notwithstanding the fact that this matrix is almost non-invertible, and if we find out that the ratio of lowest to highest eigenvalue is very low, we know straight away that we are trying to estimate too many parameters. So we have to redo our manual regularization. This all becomes very painful, doesn't it? So what we can do then but where it does become convenient is that the composition of the eigenvector which corresponds to the highest eigenvalue can tell us what is wrong with the inverse problem as currently posed, and therefore what is wrong with the manual regularization that forms the basis for the inverse problem that we are currently trying to solve. So suppose that we discover that our lowest to highest eigenvalue ratio is very low. Say it's down around 10 to the minus 6 or 10 to the minus 7. Then we know we have a problem. PEST was lucky to invert that matrix that it has to invert. So we look at the eigenvector corresponding to the lowest eigenvalue. And suppose in that eigenvector it's always normalized so the sum of its squares will add to 1. Suppose that in that eigenvector two components dominate, the components pertaining to parameters p1 and p2. Suppose they dominate the eigenvector corresponding to the lowest eigenvalue, and suppose that they are of opposite sign. Then this is what we've got. P1 plus P2 can be estimated, but not P1 and P2 individually. we know we've got to fix one and estimate the other if we're going to formulate a well-posed inverse problem. Conversely, if we look at the eigenvector corresponding to the lowest eigenvalue, and if that ratio of lowest to highest eigenvalue is very small, we know, and if that eigenvector, if its components are dominated by two parameters and they both have roughly the same value and roughly the same, and they have the same sign, then we've got this situation. P1 minus P2 can be estimated based on the information content of the calibration data set, but not P1 and P2 individually. Hence we must fix one and estimate the other when we redo our manual regularization. Or if we have a situation where the eigenvector corresponding to the lowest eigenvalue is dominated by only one parameter, then we have this situation. No model output corresponding to members of the calibration data set is sensitive to that parameter, therefore it's inestimable. We have to supply a value for that parameter ourselves. It cannot be estimated on the basis of the calibration data set. I'd like to say a few words now about prior information. Suppose that we know something about the parameter values directly. Suppose that we have intuitive knowledge of their values, born of expert knowledge. Or suppose that we have some measurements of their values, these measurements being an outcome of site characterization. There is no reason why this intuitive knowledge, this expert knowledge, or these direct measurements of parameter values should not be included in the solution to the inverse problem. This is easily done through expanding the problem to include them. So I may add, for example, relationships like this with an expanded set of measurements and a correspondingly expanded X matrix and weights applied to these extra entries in that X matrix. I may, for example, suggest to the inversion problem that P1 equals this value here. I may feel that P2 and P3 should adhere to this relationship unless the field data, unless the measurement data set says differently. So, as long as these relationships are linear, they can be included in extra rows of this X matrix and thereby form a component of the solution to the inverse problem. And in doing so, this can bring some obvious benefits with it. Firstly, by adding extra data, even though this data is in fact estimates of values for parameters or of relations between parameters, that extra information may take a problem which is bordering on being ill-posed and make it well-posed. This may create greater numerical stability in the inversion process, as the matrix which I have to invert is now much easier to invert. The other thing too is that there's an obvious benefit in putting expert knowledge into the mix when trying to estimate parameters. I can't ignore my expert knowledge, nor should I. And if I have direct measurements of system properties, of course they should figure in solution of the inverse problem. Unfortunately, however, when we're solving an inverse problem based on manual regularization, we can run into problems. And that's one of the reasons why manual regularization as a methodology for calibrating a groundwater model, in my opinion, is not the best way to calibrate that model. A large problem with using prior information is what weight do we put on that all-important information. If the weight is too large, then PEST will simply ignore the field data, and the values estimated for parameters will be entirely those that are an outcome of prior information. Therefore, I won't get a good fit with the calibration data set because I've put too much weight on something that I may not be sure of. If I put too little weight on the prior information, it will be ignored and serve no purpose. If I have direct measurements, for example, if I've done a pumping test in a large zone which I've said is entirely constant in its values because that's an outcome of my manual regularization strategy, how relevant is a point measurement of a system property to a large zone-based parameter, large and zone-based, because that's my mechanism that I chose for manual regularization. So there's a problem here in that manual regularization demands lumping and averaging of parameters, and this tends to make it difficult to include point estimates of values of parameters in the inverse problem. And then we come back to the problem of weights. Ideally, this is the formula that we use to ascribe weights to measurements comprising a calibration data set. The same formula, ideally, should be used applying weights to prior information. But what is the uncertainty of intuition? What is the uncertainty of a point measurement applied to a large zone? These are difficult or almost impossible problems to resolve, and hence make incorporation of expert knowledge or point measurements of system properties in an inverse problem that relies on manual regularization very difficult. So let me finish with some conclusions on manual regularization. As I have said, I don't think that this is an ideal way to calibrate a groundwater model. The hydraulic properties through which groundwater flows are extremely heterogeneous and are characterized by many parameters. Yes, we have to regularize, but methodologies presented in other videos that are an outcome of mathematical and numerical regularization can do a far better job as helping us attain a minimum error variance solution to that inverse problem than manual regularization. Manual regularization relies on subjective parameter simplification. I won't know whether I'm estimating too many or too few parameters till I find out whether I'm overfitting or underfitting. And when I have fit my data, it's very difficult to provide a guarantee that the regularization, the manual regularization methodology that I've employed to attain a well-posed inverse problem leads to a solution of that problem which is of minimum error variance. I have just discussed the difficulties of including expert knowledge and direct measurements of system properties in an inverse problem that is an outcome of manual regularization. And then there is the problem that once I have achieved what I hope is a minimum error variance solution to that problem of calibrating a model, I then have to add extra parameters if I'm going to do uncertainty analysis, particularly if I'm analysing the uncertainties of predictions which may be sensitive to details of hydraulic properties, the very details that I have to eliminate if I'm going to perform manual regularization. For the fact that these properties are inestimable makes a substantial contribution to the uncertainties of predictions which depend on them. Therefore, these inestimable properties and inestimable combinations of parameters need to feature in the uncertainty analysis process if the uncertainties of predictions which are sensitive to them are going to be well characterized. All in all, putting all this together, manual regularization is, to me, an unsatisfying process. Hence, the subject of other videos will be how we can achieve uniqueness through mathematical and numerical means of regularization, and how achieving uniqueness through these means puts us in a good position to thereby explore post-calibration predictive uncertainty. That, as I say, is a subject of other videos. Thank you.